moving on to a new section. And this new section is not part of week 2's homework. So it's not due on Sunday and it will not be part of your online test too. But I would suggest you do as much of this homework as you can find time for to make next week's homework a lot less. So we are going to be looking at section 2.5, limits where infinities are involved. So if you can think back to when you were doing 141, can you remember vertical and horizontal asymptotes? Remember those guys? That's essentially what we're going to be doing here. We're just going to introduce limits into the mix. So we're going to look at our vertical and horizontal tangent lines, but we're going to look at them in the sense of as limits, right? So here we have a horizontal asymptote at y equal 2. So first kind of questions we're going to be answering, there are not many of them, is finding the limit as x tends to infinity of a function or as x tends to negative infinity of a function by just looking at a graph of it. So if you see this one here, that red horizontal line, right, is called a horizontal asymptote. It's got really weird spelling as well. So horizontal asymptote. That's that guy. That basically says, look, as the values of x get bigger and bigger and bigger, this function levels off at a y value of 2. And the answer to what is the limit as x tends to infinity of a function is just that number. That makes sense. As x gets bigger and bigger and bigger, won't the value of the function, which is essentially the y coordinate of its graph, get closer to 2? And in this particular question, you can also go the other way. What happens when x gets infinitely large? Well, in this particular question, the answer is also 2. You can, however, get this situation. Right, and if you're looking at this particular graph and you're being asked to use it to find the two limits, they are now not going to be the same. The limit as x gets to positive infinity is 1, but the limit as x gets to negative infinity, which is going this way, is negative 1. So it is possible for these two limits to be different from each other. Agreed? It can happen. Some graphs, that's exactly what you get. And there is a third possibility. Okay. The limit of this function as x tends to negative infinity is what happens to the graph as it's going this way. And can you see it's leveling off at the horizontal asymptote -3? What is happening to the limit as x tends to infinity as x goes to positive infinity? So you're going this way. Essentially, can you see that's climbing upwards forever, right? And we are going to allow infinity to be an answer. Because sometimes you would just say does not exist or undefined or something, right? But I want you to say plus infinity now when that happens, right? That makes sense? It's the third possibility. Let's look at a fourth possibility. What is going to be, if there is one, the limit as x tends to infinity of this one? It's basically the sine function. What do you think the answer should be this time? In this situation, the answer was plus infinity. That's not this time. What will the answer be this time? Any ideas? Let me phrase it differently. Is this function leveling off at any number? Is it leveling off at 2, right? Is it getting closer and closer to 2 as x gets infinite? No. Would you agree this goes up and down forever? So one last try. What do you think this limit is there, if it has one? Okay, here goes. That limit does not exist. Does that make sense? That if you travel to infinity, won't this function still go up to 1 and then back down to -1 and then away back up to 1, right? There's no leveling off at any point in this graph. And the same would be true if x tends to negative infinity. So you can have horizontal asymptotes on both sides that are the same number. You can have horizontal asymptotes where on one side it's one number and the other side it's a different number. You can have graphs where on one side it shoots off to infinity and on the other side it has a value, it levels off at a horizontal asymptote. And you can have functions that have no limit as x tends to either infinity or, in this case, actually also negative infinity. Are you comfortable about that particular way of looking at graphs to answer these questions? So, if you got a graph, would you be able to say, yeah, I could look at that and find these two limits if they exist? Okay. And I'll check that off my list. So now we're going to find these two limits by using a table of values. So suppose I went and said to you, I want to know the limit as x tends to infinity of x cubed plus, 4x plus 1 over 2x cubed minus 2x. Now, I could certainly put that into Desmos, and I would find out that it is leveling off. But the problem is, what number is it leveling off to? Because you can't really tell the horizontal asymptote because Desmos doesn't draw them. So we're going to do it using a table of values. So I'll set up an x, and then I'll put here this function. So it's going to be x cubed plus 4x add 1 all over 2x cubed take away 2x. And I'm going to use my TI-84 and I'm pressing y equals. And you type in that guy, so a bracket. Takes a little while. X cubed add 4x add 1, close the thing, divided by, do another bracket, 2x cubed, take away 2x, close the brackets. So you put this equation in. Be careful about brackets because you do need them. I shouldn't need to do this next line, but just in case for some reason you've never set up your calculator correctly for this job, blue button, second one. Check that one there, the one that says ask. As long as that's highlighted, it's good, and you never need to do it again. And lastly, you go to the table, which is right here on the last button. So second table, and rub out, second table, and rub out those guys. And now you put in a number, like 10. And the answer looks to be, let's put the answers in red, 0.526, 3 decimal places will do. And then you put in a bigger number, but not 11, put in a lot bigger, like 100. And when I do that, I get the answer 0.500. Then you put in a really big number, which I think that's 1, 2, 3, 4. One more. Put in a number like 1,000,000. And actually, the answer isn't exactly 0.5, but what the TI-84 done has basically done is that it can only work to, I think, 16 decimal places, right? It rounds off everything to 16. So the real true answer probably is 0.5, 15 more zeros and a 3, right? But it just rounded it off to call 0.5, which is really good for us because the limit of this fraction, as x gets infinitely large, can you see this foaming in on the answer? 0.5. That makes sense? So if you find the value of the function at extremely large values of x, aren't you going to get an answer that is pretty close to the limit if it exists? Try another one. Suppose I want to find the limit as x tends to, say, negative infinity, and the function that I want to do it to is x to the 4. And it's that one. Then I set up my table of values. And I'll probably pick 10. Then I'll pick 100. And then lastly, I'll pick 1,000,000. So all I need to do is go into y equals.
Being recorded.
Bracket. X to the 4 plus 2x squared. Close the brackets, that's the top. Divided by, bracket, 3x to the power of 4, take away 2, close the brackets. That's that done. Go straight into second table setup. And guess what? Since I'm using the same numbers as before, I've already got my answers. And my answers are that when it's 10, it's 0.340. When it's 11, it's 0.3334. And when it's 1,000,000, it's 0.3333. And if you go down to here and you move over to here, do you see you can see the answer that's in the table to more accuracy? I know the table only shows about 5 decimal places, but if you highlight it, can you see you get about 12? Now, same basic problem. What is the limit as x tends to negative infinity of this function? And guess who's done a no-no? So I'm going to change the question so it works. Plus infinity. Haven't I done a table for plus infinity? I'll do negative infinity for the next one. What's the limit of this fraction? It's not a trick question. I didn't quite catch what you said. It sounded right, but I didn't catch it, Joseph.
Is it 0.3?
It's definitely 0.3. Could you do more than that? More accurate answer?
Zero 0.33?
Yeah, and 0.503s. And what fraction would generate 0.33333, like for 50 of them? That's the tricky part.
A third.
I would make an intelligent, not that I am not intelligent, but an intelligent guess that that answer is probably going to be a third. Would you agree? Or 0.3 or 0. Lots of threes. I think if you want a really accurate answer, I think that would be my prediction. So let's do the table of values with a negative infinity, which is actually what I meant to do the first time. I'll do it with that one. Now, the only real difference when you want to find the limit as negative infinity is you choose negative values for the x. Y equals it really is helpful to have a calculator for these questions. So if you don't have one, you can still, I believe, get a loaner from the mesh office. You just need to talk to Cheryl Phillips. Send her an email. And say you'd like to borrow one, and she'll tell you when you can come and pick it up. And it's free for the quarter, then you take it back at the end. Okay, we got this fraction thing going. I should be able to just go to second table, rub out the other stuff, and put in negative 10. Like the answer is negative 0.08. Then I'll put in negative 100, and the answer is negative 0.008. And then I'll put in negative 0.12345. Negative 1, 1, 2, 3, 4, 5, 6. And the answer I get is negative 8e to the negative 7. Okay, let's figure out what does that mean. When you see this on a TI 84, it means you've got a very small number, and it's so small that the TI has went into scientific notation. It really means negative 8 times 10 to the negative 7, but it doesn't write that, it writes that instead. And if you're not sure about what negative that looks like, if you do that and write it down as a decimal, that basically means 7 zeros. So I go negative 0.1, 2, 3, 4, 5, 6, 7 zeros and an 8. So that guy there is actually negative 0.1, 2, 3, 4, 5, 6, 8. And when we are finding what the limit of this is equal to, it doesn't mean it's that number. We use a little bit of common sense and we say, okay, what's this number approaching? What's this giving me a clue to? And I'm looking at that, and I hope you're saying the same. Are you agreeing that's basically it's heading towards 0? Would you agree that's almost 0 already? And so the answer that goes here is 0, which brings me back to this question. Yeah, this question, that answer is 0.3333. In fact, if you did it on the screen, it's about 12 threes in a row. If you looked at it more accurately. But we're trying to say, what does the limit look like? So what number is it probably going to try to become? And in this case here, I would say it is a third, because 0 point lots of threes is a third. And in this one up here, we got lucky. I mean, the calculator couldn't handle the number because it was so darn close to 0.5. It didn't have enough zeros to be able to tell you, really accurately what the last number was. Okay, are you comfortable now that if I gave you what is the limit of this expression and you were going to do it with a table of values, do you feel comfortable you know about how to do the process? I cannot see too much in the way of happy, sad, or any kind of faces here. That's not good. Okay, I'll just pick people. Vanessa, I'm putting you in the spot. Be honest with me. Okay with this? Like some more?
So how do we, like, for the, because we just put 0 as the,
Yeah.
what would equal, like, why wouldn't we put the more specific, like the really small number?
Oh, that really small number? That's a good question. I like that. I should do that more. It's a very good question. So what Vanessa is saying is, why did you put 0 here instead of, I don't know what I would call that, a more accurate number, right? Why don't I use this number? Right? That's kind of what your question was. If I had chosen another number like negative a million, do you know this answer would have changed into, it would have changed into something like this, -7 e to the -30. Now, I'm not going to write that, but can you imagine that would be a heck of a lot of zeros? That is much smaller, and you might say more accurate answer than that, which I guess it is in one sense. But we're not interested in this value per se. We're interested in what is this heading towards? And would you agree that this number, and definitely this number, aren't they all heading towards this value? They're trying to get to 0. Remember, limits are what you're trying to get to. Even if you never quite get there, what you're trying to get. And in this case, question here, what I'm saying is that this here is trying to tell me that it's getting to 0. This one here is trying to tell me that it's getting closer and closer to a third, right? And this one is 0.5. Did that help? All right. Have we any other questions? Because if I don't get them, I'm going to have to assume that we're good. And good's fine, but sometimes you end up doing homework and then you're not sure. Okay. Take that one off the list. Now we're going to do the biggie pot one, number 3. How to find infinite limits by algebra. Right. So if you show me a graph of it, I'll tell you what the limit as x tends to infinity is just by looking at it. If you give me a question like find the limit of something, I could do a table of values and estimate it that way. But now we're going to do it through algebra. And there are going to be 2 methods that we're going to use. One's called brute force, and the other, it doesn't have a name that I know of, so I'm going to make up my own name for it. So my name is going to be dividing top and bottom method. So let's show you how the brute force method works. Let's suppose I want to find the limit as x tends to infinity of 7 over x squared. Nice simple fraction to work with. In brute force, you basically replace the x by this number. So in this case, by infinity. And then you do calculations involving infinity are a little bit different than calculations with normal numbers. I'll give you an example. 7 over infinity squared is the same thing as 7 over infinity. Would you agree if you took infinity and square it, don't you just get infinity, right? That's a kind of funny algebra, isn't it? Because 5 squared gets you 25 and 2 squared gets you 4. With the exception of 1 and 0. Don't you, when you square something, you get a slightly different answer. But you see, when you square infinity, you get exactly the same answer. Then the next thing that's a little bit different with infinity is that if you have a number, as we do here on the top, and it's 7, and there's an infinity as it is here in the bottom, that is actually equal to a number. So if you had $7 and you shared it amongst everybody in the universe, right? Essentially, wouldn't everybody get nothing? Or at least a limit of nothing. Does that make sense? So dividing by infinity gets you 0. Let's do some brute force on this one. So it's going to be 2 times infinity squared. Should be a 3. Divide, take away 7. That's going to be 3 on the top. Okay. Here's the weird algebra, right? The weird calculations with infinity. I'm going to do more lines than you would ever want to write down as working, but here goes. Would you agree that infinity squared is infinity? Right, infinity times itself. So you're going to get 2 times infinity, take away 7. What is 2 times infinity going to get you?
Infinity.
You know, I'm going to be retiring in a couple of years. I'd like to do it before this class finishes.
Infinity.
Thank you. Yes. I knew if I hung in there, you'd say it. You probably knew it, but you just, I don't know, maybe you just didn't feel comfortable at telling us, right? Isn't twice infinity still infinitely big? Now, here's one that's kind of interesting. What is infinity take away 7?
Still infinity.
Still infinity. Would you agree if you've got an infinitely, a number that went on forever, right? Bigger and bigger and bigger. Do you think taking 7 away from it's going to make any real difference to it? Nah. Doubling it just makes it bigger, right? So it's still infinity. Doesn't squaring it make it bigger? It is still infinity. Now, isn't 3 over infinity 0? So far, so good. Try this one. So it's going to be 4 times infinity, add 1 over 3. So same kind of calculations with this thing called infinity. Are you comfortable that 4 times infinity is still infinity? Right, 4 times infinity is infinity. And if you add 1 to that answer, isn't it still infinite? Still infinity. So you get infinity over 3. So this is a special kind of arithmetic, right? Dealing with infinity. What is infinity divided by 3 going to get you?
Infinity.
Infinity.
Infinity, yeah. I know that's weird because you normally, you're doing it with 7s and 22s and things are good. But when you deal with infinity, your answers are infinity or 0. Have you noticed that when you deal with infinity, the answer is infinity plus or minus or 0, right? It's 0 or it's infinity. You only have 2 choices, right? It goes left or it goes right. So if I see a calculation and there's an infinity in it and something's been done to it, the answer is going to be it's still infinite or it's now 0. Let's put in 1 with a lot of bits going on. I have 3 plus 4, oops, that's meant to say x, right? Minus 3 over x squared, and that's 2 plus 1 over x. A really weird looking fraction, but it's not that weird because it's going to happen a lot when we show you the dividing and top and bottom method. So let's put in infinity and see where it goes. We get 3 plus 4 over infinity. Take away 3 over infinity squared. And on the bottom, 2 plus 1 over infinity. Okay, what does 4 over infinity get you?
0.
And what does 3 over infinity squared get you?
Also 0.
And 1 over infinity get you 0. Are you getting more comfortable now dealing with infinities? Right?
Yeah,
It's just 0 or it's infinite, depends on the calculation. Now in this case then, don't you get 3 over 2? We good? Right, I'm getting better faces now. I'm getting nods and better faces. That makes me feel good. Means we're on the right track. I don't know. Is that enough brute force questions, or do you want to see some more before we move on to this method, which is the more common method for solving these questions? Are we good? You want to see some more? Okay, I saw some nods this time. Well, the second method is a name I just made up because I don't think it's got a name for this method. It's the dividing top and bottom method. I like to give names to things that kind of give you an idea of what they're doing. Can you remember factor and cancel? Wasn't that a good name for something because it kind of gave you an idea of what the heck you were doing, right? That's, by the way, that's not a made up name. That's actually what that one's called. But I'm sure you've heard me say, as long as you do it to both sides, it's okay rule. And that's my made up name for that rule. That's not what it's called, but that's what I call it. So this is a made up name by me, dividing top and bottom method. You're going to get a question where you're being asked to find an infinite limit, right? The limit is x tends to infinity, and it's going to be maybe 2x cubed plus 4x plus 1 on the top. And it's going to be 3x cubed minus 7x on the bottom, right? So there's the guy that we're being asked to find the limit as x tends to infinity. Now, I could do a table of values on that, like we did earlier, but we're going to look at how to do it exactly. So if the answer does end up being a third, we know it's a third, right? That kind of thing. Since this one is kind of our go-to method, I'm going to set it up a little bit differently than I typically would. Step 1 is find the power of x to divide by. I can't spell today. So you look at this expression, right? There's a top part, obviously, numerator, and there's a bottom part. The power of x that you divide by is, how do you phrase this? It's easy to say it, it's harder to put it into words. On that top numerator, isn't the biggest power of x, x cubed? And on this bottom one, isn't the biggest power of x, x cubed? Right. So what you would choose is, you would choose, in that case, you would choose x cubed. Right? You divide the top and bottom by x cubed. But sometimes the top power and the bottom power are going to be different. So can you imagine that said x cubed, but this was x to the 4, right? Can you imagine a different question? When you have a choice, you choose the smaller of the two. So it's the smaller of the two, and I have to call them the largest power. Sounds like a contradiction, but what I'm talking about is, on the top isn't the largest power x cubes, and you have to pick the smaller of the two. Now in this case, they're both the same. So in this case, we are going to use x cubed. We'll come back to that. I want to make it clear what I'm doing here. If it was this one, the guy you would use would be x squared. The biggest power in each, on the top it's x squared, on the bottom it's x cubed. You pick the smaller of the two choices. Does that make sense? Because I'm not quite sure that sentence does make as much sense. If I had 3x squared minus 4, I'll make it 12, more interesting anyway. 2x to the 10 minus 2x. If I had that, biggest power x12, biggest power x10. So it's between these two that I'm going to choose. What do I use in that situation then? Which power of x do I pick?
X to the 10.
Right. Okay, does that sentence kind of make sense now? You know what I'm trying to say. Right. The power of x that you divide by is the smaller of the two larger powers, right? Larger power, right? The smaller of these two. Now in this case, they were both x cubed, so that really didn't cause a problem, but a lot of time that's not going to be the case. Now, step 2. You divide the top and bottom. You divide the numerator and denominator by x squared. So let's show you what that looks like. Here is the original limit that we're trying to find the answer to. And you divide the top and bottom by x cubed. Let's see what the fraction turns into when you do that. So you take each of these guys and divide them by x cubed, and each of these two guys and divide them by x cubed. Now, if you take 2x cubed and divide it by x cubed, you get 2. If you take 4x and divide it by x cubed, you would get 4 over x squared. And if you take 1 and divide it by x cubed, you get 1 over x cubed. Are you comfortable about what these three things look like after you've divided them by x cubed? Give you an example of me doing that. If you took 4x and you divide it by x cubed, that's what you're doing. If you cancel out one of the x's, can you see that's where the 4 over x squared came from? Right, on the bottom, divide this guy by x cubed, you get 3. Divide this guy by x cubed, and you get that. So what we've done here is we've taken the original fraction limit and converted it into this one. But now we can do brute force. On the top then, 2 plus 4 over infinity squared plus 1 over infinity cubed, and on the bottom, 3 take away 7 over infinity squared. And we've spent a little bit of time on doing the calculations, right? Algebra with infinities. So 4 over infinity squared gets you nothing, and 1 over infinity cubed also gets you nothing. And on the bottom, we have a 3. Take away, isn't 7 over infinity squared also going to get you nothing? So the answer is 2/3. Do you like that method? I mean, it allows us now to find the exact value for a limit at infinity. Okay, so it's really only got 2 steps, isn't it? Find the power of x that you're going to divide by, then off you go in step 2 and you do it. Okay, here's another one then. Let's do the limit as x tends to infinity. 3 over x to the 4 plus 2x minus 1. And on the bottom, 2x to the 5 plus 3. What power of x will I divide the top and bottom by? Look at this. What power of x?
The 4th power.
I agree, right? You got a choice between that one and that one. And the rule is pick the smaller one. So I'm going to divide the top and the bottom by x to the 4. Now, I'm pretty sure after a while you might skip some of the lines of working that I'm doing here. And that's really your choice about how many lines you really need to write. Maybe at the beginning, until you get comfortable, you write 5 or 6 lines and then it turns into 4. You know. Right, if you divide this guy by x to the 4, you're going to get 3. If you divide this guy by x to the 4, you're going to have 2 over x cubed. And if you divide this by x to the 4, you're going to have negative 1 over x to the 4. Now, oh, this one's a little bit interesting. What do you get if you divide 2x to the 5 and you divide it by x to the 4? What's left?
$2x.
Agreed. If you wanted to do a little bit of side, you know, working on the side, scratch paper kind of thing, you might say to yourself, okay, 2x to the 5 divided by x to the 4. That really just means 2x to the 5, x to the 4 on the bottom. Oh, a lot of cancelling, 1x left over. There, do you see the 2x? Kind of what you do in your head, or you're doing a bit of paper if you want. Now, once you've done this dividing, isn't the next bit just brute force? So let's see what we get. We have 3 plus 2 over infinity cubed, take away 1 over infinity to the 4, and then it's 2 times infinity on the bottom, plus 3 over infinity to the 4. Okay, and we're hopefully getting a little bit more comfortable with calculations involving infinity. So I've got a 3. 2 over infinity just gets me to 0. Minus 1 over infinity gets me take away a 0. Okay, what does 2 times infinity get you? 2 times infinity, what does that get you?
Infinity.
Infinity. Remember the rule that when you're dealing with infinity, aren't the calculations 0 or infinity? Plus or minus, I guess, right? And would you agree that 3 over this guy gets me 0? So if I tidy up a little bit, I'm now at that point. Okay, what does 3 over infinity get us?
0.
0. So the limit of this one would be 0. Okay, I know we've only seen 2 here. Are you beginning to get the flow of how this process works? And I kind of like that name. I might keep it. Does the name dividing top and bottom method, does that name help when, if I say it in the future, we're going to use the divide top and bottom method? Will that kind of help you see what we're doing here? If it's not a good name, I can always change it. But that's the one I've got right now. Right. Put your last name down for